Concrete structures inevitably develop microcracks due to tensile stress, thermal cycling, and drying shrinkage. These fissures significantly increase the permeability of the concrete matrix. Water ingress through these cracks facilitates the transport of aggressive agents, primarily chlorides and carbon dioxide. When chlorides reach the embedded steel reinforcement, the passive protective layer of iron oxide breaks down. This initiates electrochemical corrosion. The resulting rust products occupy a volume significantly greater than the original steel, generating immense internal pressure. This pressure causes spalling, which is the flaking of the concrete cover, accelerating structural degradation and drastically reducing the service life of the infrastructure. Maintaining the integrity of the protective concrete layer requires autonomous repair mechanisms to counteract this continuous degradation cycle. Self-healing concrete utilizing biological agents is specifically termed bioconcrete. The healing agent consists of dormant, spore-forming bacteria, typically alkalophilic strains belonging to the Bacillus genus, combined with a calcium-based organic nutrient such as calcium lactate. These components must be encapsulated to protect them from two critical threats: the high shear forces encountered during concrete mixing and the highly alkaline environment of the fresh concrete, which maintains a pH between 12 and 13. Encapsulation methods commonly involve incorporating the agents into porous, lightweight aggregates, expanded clay particles, or specialized hydrogels. This protective shell ensures the bacteria remain viable and dormant until water penetrates the concrete matrix through a newly formed crack. The self-healing process is triggered immediately when water enters a crack, dissolving the protective encapsulation material. This water activates the dormant bacterial spores. The activated bacteria then begin metabolizing the calcium lactate nutrient in the presence of oxygen. This specific metabolic process is known as microbial induced calcium carbonate precipitation. The bacteria convert the organic calcium source into insoluble calcium carbonate, which is calcite. The calcite crystals precipitate directly onto the crack surfaces. This mineral deposition effectively seals the fissure, restoring the concrete's impermeability and preventing any further ingress of water and corrosive substances toward the steel reinforcement. The effectiveness of bioconcrete is directly related to the width of the crack requiring repair. Bioconcrete systems are typically engineered to autonomously heal microcracks up to a maximum width of 0.5 millimeters. Cracks exceeding this threshold often necessitate manual intervention because the volume of precipitated calcite is insufficient to bridge the gap, or the nutrient supply is exhausted before the crack is fully sealed. Performance is also critically governed by the long-term viability of the encapsulated spores, which must survive in a dormant state for several decades. Furthermore, the availability of oxygen within the crack is necessary for the aerobic metabolic reaction to proceed successfully. Integrating self-healing agents into concrete requires careful consideration of standard construction practices. The encapsulated healing agents are introduced into the concrete mixer as a specialized admixture, similar to incorporating fly ash or plasticizers. The primary challenge during production is ensuring the protective capsules remain intact despite the mechanical stresses generated by mixing and pumping operations. Bioconcrete can be successfully used in both cast-in-place applications, such as foundations and slabs, and in precast elements manufactured off-site. While the initial material cost is higher than conventional concrete, this increased investment is offset by significantly reduced lifetime maintenance costs and extended structural durability, particularly beneficial for critical infrastructure projects. Self-healing concrete offers significant advantages in infrastructure where repair access is difficult or environmental exposure is severe. Marine structures, including piers and seawalls, benefit immensely from self-healing concrete by mitigating chloride-induced corrosion, which is the primary cause of premature failure in coastal concrete. Underground structures, such as tunnels and basements, utilize self-healing concrete to prevent water leakage and hydrostatic pressure buildup against the structure. Bridge decks exposed to de-icing salts and frequent freeze-thaw cycles also benefit from the continuous sealing of surface cracks, which prevents the deterioration of the concrete matrix and protects the underlying steel reinforcement. Bioconcrete represents one approach to self-healing concrete. Alternative methods rely on chemical encapsulation systems. These systems typically involve embedding microcapsules filled with polymeric healing agents, such as epoxy resins or polyurethane, directly into the concrete matrix. When a crack intersects a capsule, the agent is released and polymerizes rapidly upon contact with the air or a catalyst embedded nearby, effectively sealing the fissure. Polymer-based systems generally offer faster healing kinetics than biological systems. However, chemical systems are typically limited to a single healing event, whereas bioconcrete, provided sufficient nutrients remain available, offers the potential for multiple repeated healing cycles throughout the structure's lifespan. Self-healing concrete is currently transitioning from specialized laboratory research into large-scale pilot projects and targeted commercial applications. The primary barrier to widespread adoption in general home building remains the high initial material cost associated with producing and incorporating the encapsulated agents. Future research focuses intensely on optimizing the encapsulation material to ensure bacterial spore viability over 50 to 100 years and developing highly cost-effective nutrient sources. Standardizing quality control protocols is essential to guarantee consistent healing performance across diverse climatic conditions and construction environments before mass market integration can be successfully achieved.